Okay, so for the sake of the story, now I'm going to use a slightly different example. So originally, I took this iris data set and I extracted just 2 out of the 3 species that were separable, linearly separable. So now I'm going to extract different species. So one of them is the same and the other one is different. So instead of setosa, I'm going to use versicolor. And now, if you look at the plot, you will see that no matter how you try to separate these classes, it is impossible. So there doesn't exist a line that clearly separates the 2 classes. So what do we do in that case? So, and in such a case, the idea is that if we cannot separate the classes just clearly and perfectly, then we will allow some we are going to tolerate some misclassification. So if this is our separating hyperplane, that along the so on the either sides of the margin, we're going to say that it is okay to misclassify here, right? So okay to make mistakes within the margins. Misclassify. Okay, so it is okay to misclassify, but only within the margins. That's the main idea. All right, so let us look at the optimization problem again, right? So if we could separate the classes perfectly, then it means that we solve this optimization problem. So we minimize the square norm of the vector W subject to this constraint. And this constraint tells us that all the training observations are on the correct side of the margin. Well, so here we have bigger than or equal to 1. Right? So how do we allow for some misclassification? So basically, instead of bigger than or equal to 1, I'm going to write bigger than or equal than 1 minus epsilon I, where this epsilon I is a non-negative number. And now, if epsilon I is bigger than 1, then I allow for misclassification. Because if epsilon I is bigger than 1, so let me write it. If epsilon I is bigger than 1, then this becomes 1 minus something that is bigger than 1. The whole thing is going to become 0, which means misclassification. Right? And we're going to do it by just modifying our optimization problem a little bit. So instead of solving this original optimization problem, we are going to solve a slightly different optimization problem. And the idea is that this epsilon, it allows for misclassification. And basically, but we do not want too large misclassification, right? So we want the sum of all these epsilons to also be as small as possible. So which means that we are going to take the sum of epsilons and add it as a regularization term to our objective function. Right, so we're going to relax the constraint. So instead of bigger than or equal to 1, our constraint is going to be bigger than or equal to 1 minus epsilon I. And the objective function is going to get a new term, so which is basically something like regularization. And this C here means the cost of misclassification, right? So since the sum of all epsilons, it tells us how much we misclassify this information. So the multiplier here, the C, it is the cost of misclassification. If it is large, it means that, you know, it is expensive to misclassify as compared to change in W. And if C is small, then, you know, it is basically cheap to misclassify. So hypothetically, it means that if we take the limit of the solution of this classification problem as C approaches infinity, then we are going to get the maximal margin classifier. well, note that it is impossible to take the limit in the objective function. It just doesn't make sense, because then the objective function will be just infinite. Yeah, so it's impossible. But it is possible to hypothetically solve it for every c, right, and to take the limit of the resulting vector w. Right, so this c is the hyperparameter representing the cost of misclassification, and of course, you can imagine that as any other hyperparameter, it can be found or tuned by cross-validation. Well, the solution to this minimization problem is again going to be a linear combination of some of our vectors, so not all of them, just some of them, and these are support vectors. So these are support vectors. And these support vectors, they are points on the margins and between the margins. Now, here is the final classifier. Well, I guess it's just very similar. So it's basically the same thing as the final classifier for the maximal margin problem. So it's just that it is found differently. So the optimization problem has a higher dimension. So we need to optimize more. So not just W's, but also epsilons. But these epsilons, they do not, in fact, appear in the final classifier, right? So, and the difference is that since now we are going to tolerate some misclassification, it means that some training observations are allowed to be strictly between the margins, right? So these are the points that are either on the margins or between the margins. So here, 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 here. And some of them are misclassifications. So like these two are misclassifications, and these two are misclassifications. So it means that for these points, their epsilon i's are going to be bigger than 1. Well, and some points are within the margins, but so they are on the correct side of the hyperplane, but they are within the margins. It means that for these points, their epsilon is bigger than 0, but smaller than 1. Okay, so please do the quiz now.